Hello friends, welcome to another lecture on mathematical techniques in materials research, where we attempt to relate certain mathematical concepts to the metallurgical behavior or behavior exhibited by different materials. Now, in this lecture, we will try to revisit certain concepts that we have looked into in our previous session, and we will try to build on it. Now, the previous lecture was largely confined to, or we focused on defining what a derivative is, and this definition was restricted to a specific form of a function. So we considered a function, a straightforward function, which was principally governed by a single variable. So we considered a function f of x, and this function is principally dictated by, or essentially it is dictated by, a single independent variable x. And if we treat this entire function as another variable y, so y is the dependent variable which is dictated by, which is influenced by the independent variable x. Now, using this function, we try to define what a derivative is. So derivative in its general sense is the rate of change of a function with respect to the variables that influences it. So in this context, for a univariate function, so these functions or these categories of functions are referred to as the univariate functions. For univariate functions, the description becomes rather straightforward. It is how the function f of x changes as you change the x values. So using that description, we were able to arrive at an expression for the derivative of f of x. So the derivative of f of x based on the description alone, that is the change in the f of x as x changes, we were able to arrive at this expression, that is x plus delta x minus f of x by delta x. So this expression, in when we say x plus delta x, what we are essentially considering is the change in the independent variable, and delta x here considers how much the change has occurred. So by taking the ratio of how the change influences the function and how much is the change, we were able to arrive at an expression for the derivative. And since this expression is essentially based on the definition of the derivative alone, we have introduced this approximation sign here. So this is not an equal sign, this is an approximation sign, because we have brought, or we have arrived at this expression principally considering, or just by considering, the definition of the derivative. Now when we want to have an accurate description, an accurate expression for the derivative of f of x, we need to introduce a specific condition, that is limit x delta x tends to 0. When we introduce this specific condition, then the same expression becomes more accurate. So by introducing this condition, we are making this expression more accurate. So what essentially this condition does is, so when we are considering the derivative, when we are considering how the f of x changes, we are considering two consecutive points, so x and x plus delta x. Now when we assume that the distance between the two consecutive points are 0, we are rather narrowing down. We are making a precise estimation of the derivative. So when we assume that the delta x separating the 2 points is close to 0, then we are making a precise estimation of the derivative of f of x. Now a critical role, one of the critical role that is played by this condition here is that this ensures that even though the derivative of a function might change with x, this function helps us realize it. So the independent variable, it influences the function. So based on the independent variable, the function changes. In addition to the function, it also influences the derivative. In most cases, it also influences the derivative of the function. This delta x tends to 0. This condition ensures that it enables us to realize the change in the derivative as the x changes. So the x influences the derivative. Depending on the x, the derivative of the function changes. So this delta x helps us realize this variation in the derivative as the x changes. Now in the previous lecture, we considered a specific category of materials that allowed us to calculate the derivative without getting into all these operations, without doing all these. So even though these are the generalized expression for estimating derivative of univariate function, without getting into all these, we were able to calculate the derivative for a specific category of materials. So this specific category of materials, we refer to it as the unary materials or the unary system. So what distinguishes this particular material from all the rest is that these are pure forms of material. These are pure metals. It can be pure metals or it can be pure non-metals, but this system is pure. It doesn't have any other solute or it doesn't have any other component associated with it. So if it is a metal of iron, so if it is a system of iron, it comprises of just iron alone. Now, the free energy of such a system is then, in addition to being, so supposing the free energy of that system is governed by, say, temperature, pressure, volume, and so temperature, pressure, and the concentration, when we assume that all the other variables are constant, then the free energy of the unary system is solely or exclusively governed by the concentration. So you have different variables that govern the free energy of the unary system. We assume that all the other variables are constant. So the only variable that then dictates the free energy is the concentration. Now again, in the unary system, which is pure in itself, so which is characteristically pure, the only role the concentration plays is dictating the size of the system. So when you add to the concentration, you are increasing the size of the system. When you remove the concentration, when you decrease or when you decrease the concentration, you are then shrinking the size of the system. So essentially the only role the concentration plays is increasing or decreasing, or it influences only the size of the system. So therefore it is rather reasonable for us to consider the free energy of an unary system. The free energy of a unary system is directly proportional to the concentration. So in unary system, the concentration, it just decides the size of the system. When you increase the concentration, you are increasing the size of the system. When you are decreasing the concentration, when you are removing the concentration, you are decreasing the size of the system. So therefore it is reasonable for us to assume that the free energy, so if we consider that the free energy of such a unary system is directly proportional to concentration, and when we replace the proportionality sign with a constant, then we end up with an expression such as this. The free energy of a unary system is the product of the concentration and a constant. Now, when we take the derivative of it, of such a function, we end up with the constant of proportionality k. So all that we have done is we have considered a system, we have expressed its free energy, and we have taken the derivative of the free energy with respect to the concentration, and we end up with a constant here. Now, in addition to this expression here, it is also possible for us to calculate, or it is also possible for us to arrive at an expression for this constant of proportionality from this expression here itself. So in addition to taking the derivative from this expression here itself, it is possible for us to arrive at an expression for the constant of proportionality. So all we need to do is take the c and place it here. So the constant of proportionality is nothing but the ratio of the free energy with respect to the amount of the concentration, the amount of components that is present in the system, or with respect to the size of the system. And this ultimately leads us to the molar free energy. So the constant proportionality constant is nothing but, in this case, it is the molar free energy. So what we observe is, for such a function wherein the free energy is directly proportional to the concentration, wherein the univariate function is proportional to the independent variable that influences it, there are two ways of arriving at the constant proportionality. So this constant of proportionality that relates the function to the independent variable, in this case free energy to the concentration, there are two expressions that are possible. One is the derivative of the function, and other is just the ratio of the function and the corresponding concentration. So therefore what we ultimately end up having is this constant here, it represents the molar free energy, and this is unique for this case. Now what this signifies is that whenever you have a function of this sort, whenever you have a function of the sort, that the derivative of the function is a constant. So let me repeat, whenever you have a univariate function that is linearly proportional to, this univariate function is linearly governed by its independent variable, then irrespective of where you take its derivative, the value of the derivative is constant. So irrespective, here we saw that the independent variable is, in generalized cases, the independent variable has the capability of influencing both the function and the derivative. This is the generalized case. However, when you assume a function of the sort here, a linear function of the sort, wherein the function is linearly related to the variable that dictates it, in that case, the derivative is no longer dependent on the independent variable. So here, this constant of proportionality, this derivative is not dependent on concentration. It is not dependent on concentration. Similarly, the molar free energy for this case, even though in most cases it could be dependent on concentration, but for the unary case, this molar free energy is not dependent on the concentration. It is a constant value. So when you consider a unary system, and there is a linear relationship between the free energy of the unary system and the concentration, what the derivative that we get is constant. It is independent of what the value the variable assumes. It is irrespective of what the value the variable, that is concentration or x, assumes. The derivative of it is constant. Now, there is also another feature that is associated with this derivative. So there is also another understanding or another way of describing this proportionality constant, this derivative here. Now, one way of understanding that is by relating this function to the functions that we have, to different functions that we are fairly familiar with or we might have learnt about. So these functions, they help us describe different geometrical features. For instance, we know a function of a circle, we know a function of an ellipse, we also have learnt about the function of a straight line, the function of a parabolic curve, and so on and so forth. So to begin with, let us consider the function of a straight line. So the function of a straight line is expressed as mx plus c. So this is the function of the straight line, where m is the slope of the straight line, x, of course, the variable that governs the function of the straight line, and c is the constant. Now, one way of identifying c is when we assume the x is 0. So when the x is 0, so the function when x is 0 is equal to c. So this way we will be able to estimate the constant c. So in order to distinguish the concentration from this constant c, we will treat it as c bar. So in the equation of straight line, we have a constant c that is associated with it, and one way for us to realize this constant c is assuming the x equal to 0, and when we assume the x is equal to 0, the resulting function or the resulting value of the function is the constant c here. Now when you consider this expression for the straight line for the free energy curves, when the x is 0, what it means in the context of the free energy curves or free energy relation is, we want to know what is the free energy when the concentration is 0. So what essentially we are doing is, we are attempting to relate the free energy expression to the expression of a straight line, and the expression of a straight line as a constant associated with it. In order to identify the constant, we have to assume the independent variable is 0. Now when you assume the independent variable 0 for the free energy description, when you don't have, particularly for a unary system, when the concentration is 0, what it essentially means is that we don't have any system at all. So in that case, when we don't have any system, then the corresponding f of c is 0. So that means the constant is 0. So the independent variable is 0, meaning concentration is 0. When the concentration is 0 for a unary system, again for the unary system, there is no system at all. So whenever you don't have a system, the free energy is not applicable. We will not be able to identify it. So therefore, the free energy is also 0. So that means the constant that is associated with the expression for the straight line is 0. So ultimately then, the expression for the straight line that we can use to describe the or that we can use when the constant is 0 assumes a form like this. When the constant is 0, it assumes a form like this. So what we have is here the expression for the straight line, and here the expression for the free energy curve of, or the free energy relation for a unary system. So as you can see, these equations that have been indicated, so this equation 2 and the equation 1, they are of the similar form. So that means the m is equal to k, which is nothing but the slope. So what we essentially have is, since 1 and 2 are of the similar form, then what essentially this means is that the free energy curve for the unary system that we have considered with respect to the concentration is nothing but a straight line that passes through 0. So the reason we know that it passes through 0 is because when we assume x is 0, the corresponding f of c is 0, and that makes the constant also 0, and that's the reason why we see a similarity between equation 1 and 2. So from this similarity we can state that, or we can realize that, the change in the free energy with respect to concentration it adapts a form of a straight line. When you plot the change in the free energy with respect to concentration for a unary system, it adapts a straight line, and the slope of the straight line is k, which is the constant of proportionality, and that is nothing but the molar free energy of the system. So what we have essentially done is, we have seen for a unary system, when you have a function of this form, a function that is directly proportional, that is linearly proportional to its concentration, we saw that there are two ways of describing the constant of proportionality that we use to describe this expression here. One is just by taking the ratio of the free energy to that of the concentration. The second is taking the derivative of it. Now, when we consider the equation for the straight line, so this is the equation for the straight line. When we consider the equation for straight line and we compare it to this expression here, we see that the linearly proportional ultimately leads to a straight line when you graphically represent it, and this slope of the straight line is equal to the constant of proportionality. It is also equal to the ratio of the slope of the straight line is equal to the constant of proportionality. It is also equal to the ratio of f of c by c. Now, this is one characteristic feature of having a function that is linearly dictated by the variable. So, when you have such a function, then its representation will be in the form of straight line when you consider a plot wherein you have along the y-axis the function and the x-axis you have the concentration. So it represents a straight line. The slope of the straight line, it can be, so the slope can be rather estimated by just considering the ratio of f of c and c, that is the free energy and the concentration. Or the other way is like the slope we have seen, so this particular slope can also be estimated by considering the derivative of the function, which is constant everywhere. So irrespective of what the value c assumes, so irrespective of the value, be it c1, be it c2, and so on and so forth, whatever value the c might assume, the derivative of it, the slope of the curve remains constant. So that is one other characteristic feature of having a linear relationship between the function and the variable that dictates it. So in addition to a unary system, there is another instance wherein we observe such a relation. This relation between a variable and its corresponding function, this linear relation between the variable and its corresponding function, in addition to the unary system, there is also another aspect, there is also another conceptual concepts in the metallurgical and material science realm wherein we observe this similar form of the relation. The similar relation is observed when we are considering the mechanical behavior of specifically metals and alloys. So when we are considering the mechanical behavior of metals and alloys, so the reason we have rather restricted ourselves to metals and alloys is because when you are describing the mechanical behavior using so the mechanical behavior is nothing but the response offered by a material to an imposed mechanical condition. So you impose a mechanical condition, you impose a load to a material, and you see how this material responds. So usually what you do is you take a sample and you impose uniaxial tensile loading. And when you impose the uniaxial tensile loading, you will consider what is the change in the longitudinal dimension, what is the change in the length the material offers, and what is the corresponding load that is required to bring about this change. Now when you relate this change in the length of the material to the original length, you end up with strain, and when you take the ratio of the load that you impose, the uniaxial tensile load that you impose to the original construction area, you end up with stress. So now the best elegant way of describing the mechanical behavior is by considering the strain along the x-axis and the stress along the y-axis. Now, in case of metals and alloys, when you represent the mechanical behavior of using this particular plot here, the elastic region is represented by a straight line. So what essentially you are doing is you are considering metals and alloys, you are studying its mechanical behavior by imposing uniaxial tensile loading. And when the behavior is elastic, then that section of the mechanical behavior is represented by a straight line in this manner. So what the straight line indicates is that the stress is linearly proportional to that of the strain. So the stress is linearly proportional to that of the strain when the material is exhibiting an elastic behavior. Now, the constant of proportionality that relates the stress and strain is the Young's modulus. It is E. So Young's modulus is the constant of proportionality that relates the stress and the strain. So from our understanding, we can state that this Young's modulus is the slope of the curve. This Young's modulus is the slope of the curve, which is nothing but the Young's modulus is the derivative of the curve, which in this case, or the derivative of the function, which in this case is the stress. And in addition to it, this Young's modulus is also the ratio of the stress versus strain. So whatever understanding that we gained from the unary system that comprises of a single component, and wherein the free energy of the system is linearly proportional to that of the concentration, can be also extended to understand the elastic behavior of metals and alloys. So in case of the elastic behavior of the metals and alloys, you have a function of the similar form. Here, instead of free energy, we have stress that is dependent on strain, and that is of this form here. Now this constant of proportionality, it is the slope of the curve, that is the derivative of the function, and it can also be estimated just by taking the ratio of stress and specific stress and strain. So given the nature of the line here, given the nature of the elastic behavior, irrespective of the strain, be it epsilon 1, be it epsilon 2, irrespective of the strain, the slope at each and every point is constant. So when we have a linear proportionality, when we have a function that is related to its independent variable through a proportionality constant, then in that case alone, the derivative of that function is constant everywhere, irrespective of what the value the independent variable assumes. So irrespective of it, when you have a function of this sort, when you have a function of this form, wherein the dependent variable are related to the independent variable through a constant of proportionality, the slope is constant everywhere. Now, what we have so far, the whole of this discussion has so far been restricted to, or so far been based on the unary system. So we started with the unary system. We have seen what are the different ways the constant of proportionality can be estimated. So this constant of proportionality is a derivative, it's a slope, and it is also the ratio of the independent and the dependent variable. Now, and we saw that whatever understanding we have gained from that form of the univariate function can also be extended to So even though we have started with the free energy and thermodynamic discussion, it can be extended to wherever similar functions are observed. That is, in this case, we have extended it to describe the elastic behavior of metals and alloys. Now, let us move away from the initial consideration of unary system. So let us relax this initial consideration of unary system and move on to a binary system. So as the name indicates, the binary system now comprises of two components. So it comprises of, here the unary system, it comprised of a single component, so it is of a pure form. So unary system largely means a system, a material that is in its purest form. The binary system, unlike that case, we have combination of two components. So we have, generally we have a component that assumes the base role and a component that assumes a role of a solute. So when we consider a unary system, it is a pure form of a metal or any material. In case of binary system, you have an additional component to it. So when I say component, what I mean is a chemical species. It can be an element. So it can be a metal or it can also be a non-metal. So generally, when we talk about binary system, in the context or in the metallurgical context, what we mean is an alloy. So an alloy or a binary alloy, it comprises of a base metal and an alloying element. So since we are considering a binary system, we are considering one base metal and one alloying element. So it can also be, when you want to have a generalized system, when you want to have a generalized description for a binary system, so such system comprises of a solvent, one principal solvent and one solute. So we have one solvent, one solute, or one base metal, and there is an alloying element. So a simplest example for a binary system is steel, wherein the Fe assumes the role of the base metal and the alloying element is the carbon. So what we essentially have is, we are now moving away from unary system to binary system. So in the metallurgical context, one of the easiest examples that we can think of is an alloy, a binary alloy. So this binary alloy comprises of a base metal. For example, steel, you have iron as the base metal and the alloying element is carbon. And if you want to have a generalized description, the solvent is this iron, and so we have a one solvent and a one solute system. And you can also treat the Fe as solvent and the carbon, that is the iron as the solvent and the carbon as the solute. So in that case, what we end up having is solid solution. So the another way of describing an alloy is also solid solution, wherein the solvent, the larger portion of it comprises of iron and there are traces of carbon that is present. Now when you want to describe the free energy of such a binary system, so when we describe the free energy of the unary system, we described it as this. So in this case, when we want to describe the free energy of a binary system, generally we need to include two concentration. So for unary system, we consider only one concentration. Now in case of binary system, we need to include two concentration: the concentration of the base metal and the concentration of the alloying element. So the concentration of the base metal, let us assume it to be Cb, and the concentration of alloying element, let us assume it to be Ca. So what we need is, when we extend our understanding, so for unary system, it comprises of single component, so we have a function that is based on C alone. So when you extend that understanding, then the expression for the free energy of binary system should include the concentration of base metal and the concentration of the alloying element. So Cb is the number of moles of B present in the system, and Ca is similarly the number of moles of A that is present in the system. So we need to, when you extend our existing understanding of a function, a free energy function that describes a system, then for binary system you need combination of the concentration of both base metal and also alloying element in order to describe the free energy of the system. So both these variables, they dictate the function. So both these assumes the role of the independent variable. When I express the function, the free energy function in this way, both Cb, that is the concentration or the number of moles of base metal, and Ca, the number of moles of alloying element, both are variables that dictate the function, the free energy function here. Now, when we want to plot the free energy function of this form, then we need to have a three-dimensional representation wherein we include the concentration of the base metal, the concentration of the alloying element, and also the corresponding free energy function. So we need a system of this form to describe the free energy of such a binary system. Now, if we are able to rather simplify this function here, then the way we handle the overall free energy becomes rather straightforward. So let me repeat. What we now have is a function that is essentially governed by two independent variables. Now, if we are able to reduce this function, so this is referred to as the bivariate function. Because it is governed by two variables, we refer to as the bivariate function. Now, if we are able to reduce this function to univariate function, if we are able to reduce this function to univariate function, then handling it will be much easier. So what I mean by handling it is, so simplistic case. For instance, if I want to plot how the free energy changes with the concentration from 3 dimension, I will be able to move on to 2 dimension. If I am able to translate this bivariate function to a univariate function, if I am able to transform this bivariate function to univariate function, then the way I am able to handle this function, to put it simply, the way I am able to describe this function, move from a 3-dimensional setup to 2-dimensional setup. So this is something what we refer to it as. So this is rather an easiest way. So we are considering an easiest case, but if we are able to do that in a more complicated system, we refer to this as dimensionality reduction. So what we want to do is we want to introduce dimensionality reduction, and what essentially we are trying to do is change a bivariate function to univariate function. Now, one way of achieving this without losing any principal characteristic, any feature of the function, one way of translating a bivariate function to univariate function is to show that Cb and Ca, the concentration of the base metal and the concentration of the alloying elements, these are not two independent variables, these are not two independent variables, but these are interdependent on one another, interdependent on each other. So when we are able to show that Cb and Ca, these are not two independent variables, but value of one depends on the other, then it becomes rather, then using that we will be able to change this bivariate function to univariate function. So what we essentially want to do when we want to have the dimensionality reduction, when we want to reduce the complex form of an expression, so bivariate form to univariate form, what we essentially want to do is when we want to reduce the two independent variables to one independent variable, we need to show that both these variables are dependent on each other. So as there could be a linear dependency, there could be an inverse dependency irrespective of it. Once we are able to establish a relation between these two variables, then we can, using that relation, we will be able to replace these two variables with one. So thereby translating a bivariate function to univariate function, thereby establishing a dimensionality reduction. That makes our job rather easier to handle it in the subsequent cases. So it is possible for us to have a bivariate or multivariate function, and given our understanding of what is the system we are dealing with, we could be able to reduce the number of independent variables that dictates the system. So this is possible only when rather we are able to relate the function to a given system. So we would be able to reduce, we would be able to achieve the dimensionality reduction. We will be able to reduce the number of independent variables only when we are able to relate the given function to the system. So let us see if it is possible for us to relate this function to a system and then establish and then show that these two values are interdependent, and then rather introduce this dimensionality reduction. So we have a function that is on its surface, it looks like it is governed by two independent variables. Now what we want to do is, we want to relate this function to a material system to see if there is any dependency between these two perceived independent variables. So in order to do that, so when we consider a system such as this, a binary system such as this, now it is possible for us to have two different forms of these binary systems. So it is possible for us to have an open system. An open system is one wherein any time a mass transfer is allowed into the system. So the boundary of the open system is in such a way that a mass transfer across the system is allowed. So we don't have any control over what is the concentration or what is the content that is present in the system. When you have an open system, what we are essentially allowing is mass transfer at any point. So when you allow the mass transfer at any instance, when you allow the flow of mass in and out of the system, we don't have any control over the content that is present in the system. So what I mean by content is CA and CB, we don't have any control over it. So therefore, establishing that these two variables are interdependent in an open system is quite difficult. So we have a system that comprises of a base metal and an alloying element, and now this system is open. It means the base metal can flow in and out, and so can the alloying element. So in such a case, it becomes rather difficult, rather close to impossible. Unless otherwise we know the flow, it becomes difficult for us to describe or to show that these two concentrations are interdependent. On the other hand, if we assume a closed system, so the closed system is opposite to the open system. It means it is separated by a boundary, and this boundary will not allow any mass transfer to occur. So in that case, the closed system, what it means is that the total number of moles of components, the total number of moles of the base metal and the alloying element that is present, the total number of moles of the base metal and the alloying element that is present in a system is constant. So for a closed system, the total number of base metal and the alloying element is a constant, so it can be represented by a C like this. So we have established, by considering a specific form of a system, a relation between the number of moles of B and the base metal and the number of moles of A. That is, when you have a specific form of a closed binary system, when you have a closed binary system, the total number of moles of the base metal and the alloying element that is present is equal to the sum of the base metal and the alloying element, number of moles of base metal and the alloying element, and this is constant. So this relationship has now established, so this expression has now established a interdependency between the base metal and the alloying element. So what we have done is, so essentially let us see what we have done to arrive at this expression here. So in order to arrive at this expression here, we began with a binary system, and on the surface of it, we perceive that the free energy of this binary system, it is governed by the concentration of both the components, that is the base metal and the alloying elements. Now, this is the generalized case. So whenever you have a binary system without any qualification in addition to that, just we are saying that we have a binary system, then in a generalized case, the free energy of the binary system is dependent on the concentration of the base metal and the concentration of the alloying elements. Now, we are narrowing down, so using our knowledge of thermodynamics and the definition of the system, we are narrowing down, or we are considering a specific system. So when we are considering a specific system, that specific system that we are talking about is a closed binary system. So when we have a closed binary system, it means the sum of the number of moles of the alloying elements and the base metal is always constant, because in a closed system there is no mass transfer that is permitted. So in that case, this relation is introduced. So when we introduce this relation, what we have essentially established is CB and CA are interdependent. So these are not distinct variables or distinct independent variables, but they are interdependent with one another. So there is an elegant way of rather addressing or handling this expression here. So we can even work on this expression and make it even more simpler. So what we can do is take the ratio, so bring this sum of all the number of moles, the total number of moles of component present in the closed system, to the right hand side. So this will be adopts this expression can be written in this way. So what we have is the number of moles of the base metal plus the number of moles of the alloying element and the ratio of the total number of moles of the components that is present in the closed system, and we can write it as this. So what each of the term indicates is what is the fraction of the base metal that is present in the entire system. So C, the denominator, is the total number of component that is present. In the numerator, we have total number of base metals that is present. So total number of moles of base metal that is present. Here in the denominator, the total number of moles of entire component that is present. In the second term, we have the ratio between the number of moles of alloying element that is present. In the denominator, the total number of moles of the entire component or the different components that are present. So what we have in these two terms is, these two terms are alike. So and what they discuss is what is the fraction of the base metal that is present in the entire system, and what is the fraction of the alloying element that is present in the entire system. And since we are discussing the amount of the base metal and the alloying element in terms of mole, what the first term talks about is the mole fraction of the base metal in the system, and the second term talks about the mole fraction of alloying element in the system. And now the mole fraction, they dictate the amount of base metal and the amount of alloying element that is present in the system. And we have now arrived at an elegant way of relating the base metal and the alloying element. So even though on the surface of it, in the generalized case, the base metal and the concentration of base metals and the alloying element, they could be two different independent variables, but by narrowing it down, by focusing on a specific system, in this case a closed binary system, we are able to establish a relation between the two variables that was initially or originally in a generalized case was perceived to be independent. Now what we have done is we have replaced the concentration from number of moles to mole fraction so as to arrive at an expression of this form that shows that the concentration of the base metal, which now is of the form mole fraction, and the concentration of the alloying element, which now is of the form the mole fraction of A, both these are interdependent. So both these are interdependent. So therefore the function that we originally perceived to be a bivariate one, that is governed by the concentration of base metal and the concentration of the alloying element, can subsequently be written as governed by the mole fraction of the base metal and the mole fraction of the alloying element. And now that we have established a relation between these two, it is possible for us to express the function as either dependent on the mole fraction of the alloying element alone or the mole fraction of the base metal. So put it simply, this bivariate function can be expressed based on the mole fraction of the alloying element alone or the mole fraction of the base metal. So the bivariate function can be expressed as now an univariate function. So what we have now seen is we were able to translate or change a bivariate function to univariate function. Now how we were able to do that? So generally, if we have not been able to establish the concentration of base metal and the concentration of alloying element, they are interdependent, we would not be able to reduce these dimensionalities. But since we have narrowed it down to a closed binary system, now we have considered a specific form of the system. Our understanding of the metallurgical thermodynamics, the thermodynamics of material, has allowed us to consider a specific form of a system, and that understanding has allowed us to translate a bivariate function to a univariate function. So our understanding of the metallurgical concepts has allowed us to introduce a dimensionality reduction. So what we essentially have done is we have considered a generalized equation, a generalized expression, and we have reduced the number of independent variables associated with it, thereby translating it from bivariate to univariate function through our understanding of the metallurgical concepts. So that is one of the goals of this lecture, that is one of the key points of this lecture, that whenever we are addressing a specific metallurgical problem, we need to have a specific or we need to reduce the generalized approach to address our specific problem. So this is one of the examples of how it can be done. So generally, when you are considering a binary system, all you need to consider, or you have to largely focus on a bivariate function. But through our assumption of, through our focus on a specific form of a system, we were able to translate it, or we were able to have an expression for, or we were able to describe the free energy of a binary closed system using a single variable alone. So this single variable, either it can be mole fraction of alloying element, or it can be mole fraction of the base metal, irrespective of it. Based on our understanding of a closed binary system, we are able to describe the free energy of it using a single variable alone. So with this, we will wind this lecture up, and we will see how, in subsequent lecture, how our understanding of the metallurgical behavior can be used to have a specific derivation, a specific formulation from, or arrive at a specific formulation from the generalized derivations. Goodbye.